Screen is visible?
No, ma'am, you have not shared the screen.
Okay, fine. Now is it visible?
Yes, ma'am, now it's visible.
Okay, fine. Thank you. So I'll start with this slide again. So how we can find the determinant for any matrix? Let's say we have a matrix of order 1 cross 1. Then the determinant of the element is element itself. If we have a matrix of order 2 cross 2, like I have 2 rows and 2 columns, then the determinant of 2 cross 2 is A11 times A22 minus A21 times A12, right? If we have a matrix of order 3 cross 3, like if we have 3 rows and 3 columns, then how we can find the determinant? First write this element here, then hide this row and column and write the remaining elements over there. This element A11 should be with positive sign. Then we'll write A12 with negative sign, because we need to write alternate positive and negative signs. So A12, then we'll hide this row and column in which A12 exists and write the remaining element in the determinant form. Same with A13, we'll hide this row and column in which A13 exists and write the remaining elements. Then we can easily find the determinant for 2 cross 2 matrix, like this B point. We'll multiply A22 times A33, this times this, minus A32 times A23, minus A12, A21 times A33, minus A31 times A23, plus A13, A21, A32 minus A31, A22. So this is the determinant for 3 cross 3 matrix, right? Working procedure that I have already explained, there is no need to explain it again. Let's discuss one example based on the determinant. Here we need to evaluate the determinant for this matrix. How we can evaluate this determinant? First of all, we'll write this element 0. Then we'll hide this row and column in which 0 exists and write the remaining element 4704 in determinant form. Then 2, this element with negative sign, and hide this row and column in which 2 exists and write the remaining 1724 in the determinant form. Same with this 3 element, right? Then we can solve this 2 cross 2 determinant easily. 4 into 4 minus 0 into 7, but it is multiplied with 0, so it should be 0. Then minus 2, 1 into 4 minus 2 into 7, plus 3, 1 into 0 minus 2 into 4. After simplification, we get this determinant, that is minus 4, right? Here we are explaining that we can find determinant with respect to any row or column. It's not necessary that we can find the determinant with respect to this row only. No, we can find determinant with respect to this column or second column or third column or second row, third row as well, right? In that case, if we are using the column, we need to write these 3 elements here, A11, A12, A13, and then for A11 we hide this row and column, write the remaining elements. For A21 we hide this row and column and write remaining 4 elements, like that, right? This is the signs that we need to use. For first element it should be positive, negative, positive. As it is positive, then this one is negative, then positive, negative, positive. So everything, every sign is alternate, negative and positive. Here we have one more example to find the determinant. Now in this question, it is beneficial for us to find the determinant correspond to second row, because 2 elements are 0. So we need to find the determinant correspond to this 4 element only. Rest 2 will be 0. So for 4, we'll hide this row and column and write 2, 4, 4, 5 in the determinant form. And 4 should be with negative sign because the first element is positive, second is negative. So minus 4 and then 2 into 5 minus 4 into 4, right? Uh, Here in it is 4 cross 4 matrix. In the fourth row we have two zeros. So it is beneficial for us to find the determinant correspond to this third row because two elements will be 0 in that case. Like here we need to find only two elements, rest 2 is 0, right? So first, because it is 4 cross 4 matrix, so first of all we'll write the determinant for order 3 cross 3 and then further for 2 cross 2, right? Now properties of determinant. Let's say we have a determinant delta like that. If we multiply this determinant with m, that means we need to multiply this determinant, any row, any one row with m. You can multiply the first row with m, or you can multiply the second row with m, or you can multiply the third row with m. Right? Similarly, you can write it for column. In that case, right? Like this, we can take 2 common from this first row. I mean, we can take 6 common from this first row and we can rewrite it in this form, taking 6 common from the determinant. The second property is determinant of the matrix is equals to determinant of its transpose. What is transpose? If we interchange the row and column 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's say we have this matrix A, right? A transpose will be 1, A, 1, 1, 2, 3 should be in first column, 4, 5, 6 will be in second column, and 7, 8, 9 will be in third column, right? So determinant of A transpose is equals to determinant of A, right? If two rows or columns of determinant are interchanged, then the value of determinant is unchanged but sign changed. Let's say the determinant of this matrix, let's say it's any number x, right? If I write, if I interchange the first and second row, 4, 5, 6, 1, 2, 3, 7, 8, 9. So determinant of this matrix is minus x only. Only the minus sign will change. The value is unchanged. If the determinant has two identical rows, then the value of the determinant is 0. Let's say if we have a matrix like 1, 2, 3, 2, 4, 6 and 7, 8, 9. These two rows are identical, same. If we take 2 common from the second row, both the rows will be same. So the determinant of that matrix should be 0. The value of the determinant remains the same when multiply of some rows or added to a particular row. The same is true for column. If we multiply the any specific row, if we add or multiply any specific row with the same values, right, then in that case the determinant will remain unchanged. What we are doing here, we are multiplying the second row with k added with first row kd and multiply the third row with l and multiply it. right? KD plus LG. Similarly, KE plus LH, right? KF plus LI, like that. So the determinant is same. So here we are few practice questions. Okay, first let me discuss these questions also, then I'll take your question. Let's say we need to find the determinant of this matrix. We can directly find the determinant by using this method 4. Just hide this row and column and write it in the remaining 4 element in that form. 2, 6, 1, 5 and 10, 2, 4, 1, 2. Right? We can solve this determinant in that way, or further it is a 3 cross 3 matrix, so we can solve it easily. But let's say if we have a matrix of order 5 cross 5 or higher order, then it's not very simple. It's a lengthy process in that case, right? So in that case, what we'll do, we'll apply some transformations like that. What transformation we are using here? We are subtracting R1 with 4R3. This one is R1, R2 and R3. So R1 minus 4 times R3. Similarly, R2 minus 2 times R3, and R3 remains unchanged. So after this simplification, we get this matrix. What is the benefit? In the in the second row, we have 2 elements is 0 and 1 element is non-zero. So now it's very simple for us to find the determinant. I think yeah, right. Similarly, in this example, it's a 4 cross 4 matrix. So if we apply this process, like by for this element we hide this row and column, write the remaining elements, then for this, so it's a lengthy process. So what we'll do, we'll apply some elementary transformations. This kind of transformation is known as elementary transformation. You can choose these transformations as per your convenience. Here if I apply R2 minus R1, this 1 will cancel, this 1 will cancel, this 1 only this A will be will remain over there, right? Similarly for R3 minus R1, R4 minus R1, right? So we get this matrix. Clear? Now it will be easy for us to find the determinant correspond to this column, because we have only one non-zero element in this column, rest elements are 0, right? So we'll expand correspond to this one, that is this, just hide this row and column and write the remaining elements, and then we'll expand it for 2 cross 2 matrix. So in that manner we can easily find the determinant, right? Similarly, in this question, we use the column transformations here. The first column is unchanged. In the second column, we apply C2 minus C1. In the third column, we apply C3 minus C1. And then we solve this determinant. Now, the next topic is inverse of matrix. Before moving towards this point, let me take your questions. If you have any question, please raise your hand. No? Okay, fine. So the next topic is inverse of matrix, and the formula to find the inverse is adjoint A upon determinant A. Now what is adjoint A? This is known as adjoint A, right? Here A11 is minor for this element. What will be the value of A11? determinant of A22, A23, A32 and A33, right? Then we'll take the transpose. This is known as adjoint A upon determinant A. This is the formula to find the inverse of matrix. If determinant is 0, then the matrix is called singular matrix, and in this case we cannot find the inverse for this matrix. So inverse of any singular matrix is not exist, right? For example, we need to find the inverse for this matrix, and this is a 2 cross 2 matrix only. We can easily find the inverse. What will be the inverse? First of all, we need to find the minors, that is A11. For A11 it is D. For A12 it is minus C. For A21 it is minus B, and A22 it is A, right? So we just substitute the values and then take the transpose. So this is the adjoint A, and determinant is AD minus BC. So A inverse is adjoint A upon determinant A, right? Here also we need to find the inverse of this matrix, right? So for first of all we need to find the minor. First of all, A11. Minor for A11 is minus 1, 1, 1, minus 1 in the determinant form with multiplication of 1. Then minor for A12 with negative sign, 1, 1, 2, minus 1. For A13 it is 1, minus 1, 2, 1. For A21 it is 1, 1, 1, minus 1. Similarly, we can find all the minors. Then we can substitute the values in adjoint A and take the transpose, right? Then we can find the determinant, and finally the value of A inverse is adjoint A upon determinant A, right? If there is any query related to inverse of matrix, please let me know. Please raise your hand if you have any problem related to inverse of matrix. Okay, fine. Then we have few elementary row and column transformations that I have already explained, but let me explain here again. Elementary row transformations, the transformation which we have applied on row only, right? Then it is known as row transformation. What kind of transformations are allowed? Interchanging of rows. Like we can write the second row at first position and first row at second position. That is known as interchange of rows, right? Then multiply any row with some non-zero constant. Here Ri means any row like R1, this is first row, times 2 means we are multiplying first row with 2, right? Next is Rija, adding a time jth row to the ith row, right? If we add two rows, after multiplying the constant a with j row and then I add with ith row, it is known as Rija, right? Similarly, corresponding column transformations exist, like interchanging of column, multiply with any constant and adding a times jth column to the ith column, right? These are the elementary row and column transformations. Here we have few example based on elementary row and column transformation. Here we have a matrix of order 3 cross 3. What we are doing, what first of all we need to apply the row transformation and then we need to apply the column transformation. What we are doing, first of all we'll divide our target is to reduce this element into 1. The first target is reduce this element into 1. How we can reduce it into 1? By dividing the first row with this element, right? So we are applying this transformation R1 by 3, means we are dividing the first row with 3. Rest rows are unchanged. Then our target is to reduce this element into 0, right? So how we can reduce this element into 0? By subtracting R1 and R2, right? So here we are subtracting R1 and R2, so this element will convert into 0. In the next step, our target is to reduce this element into 0. How we can reduce it into 0? R1, 4R1 plus R3, right? Then it will reduced into 0. This element will reduced into 0, right? So this is the elementary row transformation. Similarly, we can apply these transformations on column. If we apply the transformation on column, what will be our target? This element should be 1, this element should be 0, and this element should be 0. How we can do this? First of all, we will divide the first column with 3 with this element, right? Then we need to reduce this element into 0. How we can do this? 4C1 minus 4C1 plus C2. If we multiply the first column with minus 4 and add it with C2, it will convert into 0. Then our target is to reduce this element into 0. How we can reduce it into 0? Minus 5C1 plus C3. Then it will be 0, right? So this is the column transformation. Now the rank of matrix. What is rank of matrix? First of all, it is denoted by R, small r. In the rank of matrix, at least one minor of order R is non-zero. All minors of higher order are 0, right? So rank of matrix is defined as the highest order of a non-zero minors of A, right? It also denotes the maximum number of linearly independent rows or columns of the matrix, right? It is easy for us to find the rank of matrix by using elementary row or column transformation. But please remember, either we can use row transformation or column transformation. We cannot use row and column transformation both in a same question, right? Like in this question, we need to find the rank of this matrix. So first of all, we'll convert this element into 1 by dividing with this same element, right? Then we'll convert these two elements into 0 by using further row transformations, right? Now we can see that the number of non-zero rows, this is non-zero row, this is non-zero row, the third row, all the elements of third row are 0, so it cannot be considered as non-zero row. So number of non-zero rows is 2, right? So rank of matrix is 2. Similarly, in this question, we need to find the rank of matrix. So again, we'll convert this element into 1 and these two elements into 0, right? Now, after transformation, we can see that the number of non-zero rows is 3. So rank of matrix is 3. As we are using the row transformation, so we consider the number of non-zero rows. If we apply the column transformation, then in that case, the number of non-zero columns should be counted, right? So if you guys have any problem in rank of matrix, please let me know. Please raise your hand if you have any problem in rank of matrix. No? Okay, so let's discuss the next topic, that is characteristic equation. So first of all, let me this equation a minus lambda I x is equals to 0 is known as characteristic equation, where lambda is any constant or scalar and I is the identity matrix, right? Identity matrix is what? Only the diagonal elements are 1. So if I want a identity matrix of order 3 cross 3, I use it in that manner. If I want a matrix of order 4 cross 4, identity matrix of order 4 cross 4, we can use this matrix like that only, right? So a minus lambda I x is equals to 0. This is the characteristic equation, right? Determinant a minus lambda equals to 0 is known as characteristic equation, where a is the given matrix. For example, if we need to find the characteristic equation for this matrix, right? So first of all, we need to write determinant a minus lambda equals to 0. Determinant this matrix minus lambda, the identity matrix of same order of given matrix is equals to 0, right? Then we'll multiply lambda with this matrix, means all the diagonal will convert into lambda. Let me write here. Then 2 minus lambda 2 0, 2 1 minus lambda 1 minus 7 2 minus 3 minus lambda, right? Then we'll solve this determinant. For 2 minus lambda, we hide this row and column and write the remaining elements. Then for 2 we'll hide this row and column and write the remaining elements, and for this 0 it is 0. And after solving, we get a, as it is a matrix of 3 cross 3 order, so we get a cubic equation over there, and which is known as characteristic equation, right? For this matrix, as it is a 2 cross 2 matrix, so we'll get the quadratic equation after solving this characteristic equation, right? And if we solve this quadratic equation, we get two values of lambda, which is known as eigenvalues. The value of lambda is known as eigenvalues. Correspond to eigenvalue, we can find the eigenvectors. How we can find eigenvector? For case first, let's say lambda is 4. We get two values of lambda now, 4 and 6. So just consider any one value, lambda equals to 4. Substitute lambda equals to 4 in the characteristic equation, right? So lambda equals to 4. Then solve this equation and write two variables x1 and x2. We get two equations. If we solve these two equations, we get x1 is equals to x2. So we didn't get any exact value of x1 and x2, but we get a hint that x1 is equals to x2. Now x1 and x2 could be 5. We never know. x1 and x2 could be 6. x1 and x2 could be 30 or any number, right? So how we can write it? If I want to write x1 and x2 in the matrix form, in the column form, we can write it as 5 5. Or if I take 5 comma, it will be 5 1 1. For this case, I can write it as 6 1 1. For this case, I can write it as 31 1. So all these are same, but the number 5 6 30 is different. So we can write it in that manner: C2 times 1 1 matrix, column matrix. So this is the generalization of all the values, right? Now for second case, lambda equals to 6, again we need to substitute lambda equals to 6, then we'll simplify and get two equations. For both the equations, we can get the values of x1 and x2. We get x1 is equals to 2x2, but we didn't get the value of x1 and x2. So we can write it as in the column matrix form 1 and 2 by taking C2 as constant. So the next is Cayley-Hamilton theorem. Cayley-Hamilton theorem says that every square matrix satisfies its own characteristic equation. Characteristic equation is determinant A minus lambda I is equals to 0, right? Every square matrix, please note, only square matrix satisfy this Cayley-Hamilton theorem. If the matrix is not in a square matrix form, then we cannot apply Cayley-Hamilton theorem, right? So every square matrix satisfies its own characteristic equations. So first of all, write the characteristic equation, that is determinant A minus lambda equals to 0. Just write this matrix A minus lambda. I is identity matrix of order 2 cross 2. Then we can write it in the determinant form, and then after simplification of this determinant, we get this quadratic equation of lambda, right? This is the characteristic equation. Now Cayley-Hamilton theorem says every square matrix satisfies its own characteristic equation. That means this matrix A satisfies this characteristic equation. That means A square minus 5 should be equals to 0. So we just find A square by matrix multiplication, row into column. Minus 5, we took I over there, that is identity matrix of same order. And after simplification, we can see that A square minus 5i is 0. That means the matrix, the given matrix satisfies its own characteristic equation, but the only condition is matrix should be square matrix, right? Now in this example, find the characteristic equation of this matrix and verify Cayley-Hamilton theorem, right? So how we can find the characteristic equation? Determinant A minus lambda is equals to 0. The matrix A minus lambda matrix I, right? If we solve this determinant, we can find this characteristic equation. Now substitute lambda equals to A. So it is A cube plus 6a square minus 9a plus 4i equals to 0. So we need to find the value of a cube, a square. A, we have the value of a, I is identity matrix. How we can find a cube and a square? First of all, we need to find a square, that is a times a, row into column, then a cube, and then we substitute all the values over there, we get the null matrix. That means square matrix satisfies its own characteristic equation. If you guys have any problem in Cayley-Hamilton theorem, please raise your hand. Yes, Sudeep. Yes, Sudeep, you can unmute yourself and ask your question.
Yeah, thank you, madam. Am I audible?
Yes, Sudeep, you are audible.
Yeah, basically, I was having a query on the rank of matrix.
Rank of matrix. Okay. Yeah, please.
Yeah, so while finding out the rank of matrix, so when we're transforming rows and columns, so what should be the official steps for making them all zeros? I mean,
Okay. So
or how
let's
do we know that it can be converted to all zeros or not at all?
No, we cannot, initially we cannot identify that it will convert into 0 or not. That we need to find whether it is converting
Okay.
into 0 or not, right? So let me
Okay.
discuss this example again. What will be our ultimate target? At the end, we need to convert this element as 1 and these two elements as 0, right? This is my target. I'll start with this target that this element should be 1 and these two elements should be 0. So how it will be 1? If I divide this whole row by 6, right?
Yes.
So I am applying R1 by 6 at R1. So it will be 1 minus 2 by 6, or I should write minus 1 by 3 and minus 3, minus 18 by 6. The rest two rows will be unchanged in that case, right?
Yes.
Now my next target is convert this element into 0. How this element will, please remember we are using row transformation, right? So we need to apply all the transformations on row, right? So now my target is to convert this element into 0. How we can convert R2? We need to apply the transformation on R2, definitely. That should be R2 plus 4R1, right? So first row will remain unchanged, third row will remain unchanged, this element should be 0, then R2 1 minus 4 by 3, that is minus 1 by 3, and 11 minus 12, right? So minus 1.
Yeah.
Yes. Now my next target is to convert this element into 0. In the similar manner, on R3 we apply R3 plus 5R1, right? So this element will convert into 0 irrelevant to these two elements. I least bother whatever these elements, they can be 0, they cannot be 0, right?
Okay. Yeah.
So after all this process, we reached on this matrix, right? That
Okay,
means the all the elements of one row is 0, right? So number of non-zero rows are, number of
2.
non-zero rows are 2. So this is the rank of matrix.
Okay. So one question is how do we know that whether we can able to convert any rows to all zeros?
No,
Or
we cannot identify, like in this next question, right? Like in this next question, all three rows ultimately are non-zero. After using all the row transformation, this element is 1, rest two elements are 0. We can see that all three rows are non-zero. That means rank of matrix is 3.
okay. So how many
Initially
times
I cannot identify whether the row will convert into 0 or not. If I could identify that the row will convert into 0, I get the rank of matrix. Then in that case there is no need to apply this row or column transformation.
so how many times we will apply row transformation? Any kind of limit kind of
No,
thing is
no,
there?
no, 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 no limit is there. You need
Any
to
number of times you
you
can
need to
apply.
think. You need to think, right? After converting this 1, 0 and 0, let's say I get one matrix. Let's say 1, 2, 3, 0, 0, 4, 5, 6, and 2, 3.
Okay.
No, just a minute. Yeah, let's say ultimately after using this row transformation, what was my first target? This element is 1, these elements are 0. I reached on this matrix, let's say, right?
Okay.
Now you can say that all three rows are non-zero, right? So rank
Yes.
of matrix is 3. But if I apply on R3, that is R3, 2R3 minus R2, it will convert into 0. Am I
Yeah.
correct now? Yes. So
Yes.
in that case, your mm, rank is 2, because if you apply further row transformation, any of these two rows will not convert into 0, right? If I apply any row transformation, you are free to use any row transformation, but you cannot use like multiply the entire row with 0, right? It's meaningless, right?
Yes.
That
Yeah.
kind of transformation never exists. So except that kind of transformation, you can use any row transformation, but still any of these two rows cannot be converted into 0. That means the rank of this matrix is true, 2.
Okay.
Right? So
Yeah.
your ultimate, your first target, I mean, how you can start the question, right? Any strategy should be in your mind, that what transformation I should use. So the
Yes.
strategy is convert this element into 1, convert these two elements into 0 if you are using row transformation.
Okay.
If you are using column transformation, convert this element into 1 and convert these elements into 0. This
Okay.
is your strategy, your initial strategy, right? After
Yeah.
that, if you will reach something like that matrix, you can easily understand that what transformation further should be applied to get the rank.
Okay. Yeah. Yeah.
Yeah.
Thank you very much, ma'am, for your
Thank you.
query answer.
Thank you. Any other question?
No, thank you, ma'am.
Yeah, Sudeep, thank you. Any other student want to ask question? They can raise your hand. Fine. So let's so eigenvalue, eigenvector we have discussed. Now the next topic is consistency of the system. This topic is a bit lengthy. I cannot complete it in 15 minutes. So can we take this topic in the next session? Monica, are you there?
Yes, ma'am. Ma'am, you can better decide that whether to continue this time or next time as per the
Yeah,
requirement of the
actually
topic, ma'am.
you can see that I have around 15 more slides. So I need a minimum 30 minutes to discuss these slides. Na? That's why it's better to take the remaining part of this session in the next class. So let me go to the summary slide. In today's lecture, we have discussed the determinants, cofactors, minor, adjoint, inverse, and rank, eigenvalue, eigenvector, Kelly-Hamilton theorem. These topics today we have discussed, right? And in the next lecture, we'll discuss the consistency of the system and Cramer's rule, right? If you guys have any query, please let me know. Please raise your hand if you have any query. Otherwise, we can conclude our session here only. Okay, Monica, then bye. Take care.
Okay, thank you, ma'am, for such an informative session on maths topic. Now, if still learners are feeling any doubt, then they can post it on the discussion board.
Yeah.
Have a nice day, everyone. Have a good day.